Hi, it's Mr. Duffy. Welcome to today's lesson in physics, and today's lesson is about relative motion. Our lesson for today is really just again about saying that people from different perspectives will see the motion of an object differently. And so we're going to start off with this picture here of an airplane, and this airplane is dropping a ball. Um, if we're viewing the airplane from above, we can kind of see that the airplane and the ball are moving along. And again, the different pictures like snapshots like every second or so. Again, they're moving from the left side to the right side, and so what we can see is the ball is basically just kind of moving right along with the airplane. Again, this would take into account that there would be no air resistance and so forth, so we wouldn't see any, you know, it dragging behind or so forth. But anyways, again, they're staying right in line with each other. From our perspective, again, the ball is getting smaller because it's getting, again, we can kind of see it's getting further from us. So objects that are further away appear again smaller. But anyways, like I said, they're pretty much moving in a straight line together. If we view it from the side, though, you can kind of see that picture is not quite exactly the same. They're still moving again from left to right, but we can kind of see that the ball is taking a more of a arched parabolic path and before it hits the ground. Um, so again, different perspectives give us different um, basically interpretations of motion. We would call these different perspectives our frames of reference. So different frames of reference are giving us our different descriptions of motion. Now, here's another example, but words without a picture. If we're moving 80 kilometers north and a car passes us going 90 kilometers an hour, to you, the faster car seems like it's moving north at about 10 kilometers an hour. Again, you're seeing like the difference in speeds there. Someone standing on the side of the road, though, would measure the velocity of the faster car as 90 kilometers an hour towards the north, and then again, your velocity would be 80 kilometers an hour towards the north. So again, somebody on the side of the road would see the velocities that for again at rest. You've probably seen that example plenty of times as a car goes past you on the road. Again, it seems like they're going again really fast compared to you, or again, it's all compared to your frame of reference. So sometimes if they're again just like going the same speed, you're right next to each other. Again, it would seem like in general frame of reference, you're both not moving. Now we can take a look at this. I have a demonstration for you. So this is a relative speed. We're not going to actually solve the problem, but basically this would be kind of a scenario where you're standing on the side of a river and you're watching two boats go past. From the image here, from the simulation, we can kind of see that the red boat is obviously moving at a faster velocity than the blue boat. But again, if you were on one of those boats, you would not see the exact same. We're not going to calculate the speeds, but you would not see the same thing. Again, you would see the red boat passing you. So let's say again, you're going 20 kilometers an hour and the red boat's going 30. You're seeing the difference between them. You'd see 10 kilometers an hour as it passes you. So again, depending on the frame of reference you are, you would see again the different perspectives. So now we're going to take that concept. Those are objects moving in one dimension. Now we're going to take the concepts into two dimensions, which is again what this unit is all about. So relative motion again is just a way of saying that again people see different things from different perspective, from different frame of reference, but now we would have two objects moving. So great examples of this would be a boat traveling in a river where the boat has a particular velocity and the river also has a particular velocity because again the river's moving. Another way example would be like an airplane moving through the air. So again, the airplane has a particular velocity as it's moving, just again with the engines, but then the wind also would be blowing in a certain direction as well, and it would also give a certain velocity to the airplane as well. So in two dimensions, we would add those two velocities together to get our resultant velocity, and we'll see that in turn has some trigonometry to do, so right triangles and so forth. Now let's watch this. I didn't make this a second video, but let's watch some examples of this, of a car moving across a treadmill. So here, we're going to pause the video and go to this one.
In this clip, we're going to learn about relative motion. Sometimes a plane will be carried along by the wind and arrive at its destination earlier. Other times there's a headwind that blows against the plane, slowing it down. Sometimes the plane can be blown way off course. Now, the pilot's not even aware, maybe. He's flying through the air, he sees clouds in front of him. Meanwhile, the wind is blowing him completely off course. The same thing happens with a boat in water or a swimmer in water. And to understand what's actually happening is a very simple application of vectors. So I'm going to show you what happens in each case, and then I'm going to illustrate it by a little toy car on a treadmill. The treadmill will be like the water or the wind that's blowing, and the car will be like the plane or the boat on water. So here we go. Let's suppose I have a boat, it's still water, and it needs to move to the other side of the river. It heads directly across the river. It has a velocity that is constant. Now, here's a little car, a little motored car, battery operated, about to be placed on a treadmill. The treadmill isn't moving. So it will move directly to the other side at a constant velocity. Here it is in slow motion. It's a similar situation to the river. Now, the boat, this time, wants to move across the river. It'll move at the same velocity it did in still water, but the river is carrying it to the right. And we see that the boat is moved off course. Here's what the vectors look like. The boat has the same velocity it would have in still water as it heads directly across the river, and we call that the velocity of the boat relative to the water. We write it like that. The water is now going to carry the boat off to the right. We add them head to tail, these vectors, and this is called velocity of the water relative to the shore. That's how fast somebody on the shore sees it moving. The actual sum now is the vector sum, where I start and where I end, the velocity of the boat relative to the shore. That's what an observer on the shore would see. And notice how I write that, the boat relative to the shore. Well, here's my little car now on the treadmill. And this time, the treadmill will be carrying it off to the right. And the car will be heading with the same velocity it had before across the treadmill. When I add those two vectors, we see that the car, to an observer at the side, would move off at an angle. Here it is. Here it is in slow motion. Now this time, the boat must go across the river, directly across. However, the river is flowing to the right, so which direction should it head? And the answer, it must head against the stream at an angle. And so we add up the velocity of the boat, the velocity of the water, and I get a lesser velocity now across the water. It heads at an angle against the flow of water. Well, that's what happens. It moves across, but at a slower velocity. Now here's my little car on the treadmill, and I want it to head directly across. So the treadmill moves to the right, the car moves into the treadmill at an angle. When I add those two vectors up head to tail, I see that I get a sum that goes directly across the treadmill. So here it is. And here it is in slow motion.
Okay, so I hope that video kind of gave you, again, some good examples. We're going to go ahead and work through some math problems now then to kind of like put these relative motion problems to our kinematic equations. So here I have an example of a boat problem. So again, a boat's traveling on the river. A boat is heading north across a wide river with a velocity of 10 kilometers an hour relative to the water. The river has a uniform velocity of 5 kilometers an hour due east. Determine the boat's velocity with respect to an observer that would be on the shore. Okay, so somebody's again watching this from the shore, and I have a nice little diagram over here on the right, kind of what's happening. So the velocity of the boat with relative to the water, that was the first number they gave us. That was a velocity of 10. So 10 kilometers an hour. We can just leave it in kilometers. It's not a big deal. And then the second velocity was the velocity of the river with respect to the Earth. So that was 5 kilometers an hour. And the question is, what is the velocity of the boat with respect to the earth, or the velocity of the boat with respect to the shore, somebody that's watching from the shore? You can see this make a right triangle. Could be uh, the boat's traveling due north, the water's traveling due east. So with that being the case, again, those are 90 degrees angles to each other. We can just do the Pythagorean theorem. So yeah, 5 squared plus 10 squared equals c squared, which would be, again, the velocity of the boat relative to the earth. Comes out 125 equals c squared, square root both sides. C comes out to be 11 kilometers an hour. Okay, that's one part of our answer. But it says, again, velocity, so we need the angle there, the direction. And so to get the direction, I'm going to use my opposite and adjacent sides. So that would be tangent. So tangent -1, inverse tangent, equals opposite, 5 over 10. And that would equal our angle measurement. That comes out to be 26.6 degrees. Again, not quite done with that one yet, because what is that 26.6? Well, that would be east of north. 26.6 degrees east of north. So that would be our velocity with respect to somebody that was watching on the shore. Now, let's go ahead and take a look at one more type of problem. Again, it's going to involve a little bit more of our kinematic stuff. That one was kind of really just trigonometry. But solving for some different aspects here. So now we have a riverboat heads east on a river that flows south. The riverboat is moving 3.2 meters per second with respect to the water, and the water moves south with respect to the shore. Sorry, that should be south. With respect to the shore at a speed of, that's 4.4. There's no way it's 34.4. Okay, my copy and paste skills were not so great on this one. Now, anyways, determine the resultant velocity of the riverboat, velocity with respect to the shore. So again, somebody watching on the side of the shore. So we have the river flowing south, and the river boat is moving east. So somebody on the side of the shore would see the boat move in that direction. The river boat is moving at 3.2 meters per second, and the river is moving at 4.4 meters per second. Okay, now with that being the case, again, you can see it makes our nice right triangle here. So nothing different from the last problem. We're going to still do the Pythagorean theorem. 3.2 squared plus 4.4 squared equals c squared. Okay, we're going to, again, solve for c. So 3.2 squared plus 4.4 squared is 29.6. And then we're going to take the square root of that. And that comes out to be 5.4. So that is its magnitude, meters per second. It's the magnitude somebody would see with respect to the shore. But again, we need to find the angle then as well. So we need to find theta. I'm going to use tangent again. So inverse tangent. Opposite is 3.2 over adjacent, which is 4.4. So inverse tangent, 3.2 divided by 4.4 comes out to be 36 degrees. 36.0, so exactly 36. And again, that would be then east of south. Okay, that is nothing different from the last problem. Where it becomes different now is part B. If the river is 127 meters wide, then determine the time required for the boat to cross the river. Now, the question is, what velocity do I use? Do I use the resultant that I just found? Do I use the velocity of the river, again, with just the velocity that the water is moving? Do I use the velocity of the boat? Well, hopefully the kind of makes sense. You should actually use the velocity of just the boat, because the velocity of the boat is directly east, and the displacement here, the width of the river, is also directly east. So again, it's the width of the river, not the length of the river. So we want to use the velocity vector and the displacement vector that, again, match up, or the distance, I guess, that matches up. And so again, we want to use the east portion, which again, in this case was 3.2 meters per second. So no acceleration, velocity equals just distance divided by time. We have our velocity and we have our distance. We're trying to solve for time. So if I rearrange it, it just becomes distance divided by velocity. My distance is 127 meters and my velocity is 3.2 meters per second. So 127 divided by 3.2 equals 39.7 seconds. 39.7 seconds. That's the time to cross the river. I don't know why that's decimal points. Kind of funny. Sorry. Okay, now determine the distance the boat travels downstream. Again, it's not going to go straight across the river because the river is also moving. It's going to move a little bit downstream. So to figure out how far it's going to move downstream, we're actually going to use the velocity vector that is pointing down, south. Again, the river is making it move south. So that velocity, again, is 4.4 meters per second. And again, we're trying to find a distance here. And what we found in the last problem, again, we should realize that the length of time it takes to cross the river would be also the time that it would take to go downstream. So those times will be the same. In letter B and C, the times will be the same. And in which case, if we're solving for distance, distance would equal velocity times time. And so my velocity is 4.4 and my time is 39.7. So that will come out to be 174.6 meters downstream. Okay, well that solves for some of the two-dimensional relative velocity type of problems that you will see in this unit. Hopefully those make sense, and thank you for watching.